We're going to try and get through all of Introduction to Linear Transformations in less than 20 minutes. I don't have high hopes, because as you've probably realized by now, I like to talk. But we're going to try by still maintaining your understanding. Okay. I hate when I do that. Okay. Linear transformations. Linear transformation is a fancy way of saying a function. That's it. It's a mapping, and we call it T. And what it does is it assigns a rule that takes something from a domain, does something to it, goes into our little vector box, our transformation box. Now, I will caution you, in algebra, like in pre-calc and stuff like that, we've talked about transformations being something that you might do to shift a function, right? Up and down, left and right, you might scale it. But that's kind of exactly what we're doing here, is we're taking a vector and we're transforming it into something else. So we take our domain, so whatever our domain is, and then our output. So we're going to map things in our domain to things in something called a codomain. And so you'll notice sometimes they have the same size, sometimes they don't, and that happens. An example of domains and codomains and how that's different from what we call the range, right? So in algebra, we talk a lot about functions, and we talk about their domain and their range, right? Your domain is your set of inputs, your range is your set of outputs. Well, your range is often a subset of a larger sort of idea here. So in this case, so let's think about, we're just going to kind of, if I look at the function f of x equals x squared, right? The range here, or the domain, is all real numbers, right? So every single real number on the Cartesian coordinate system. So it's everything in the real numbers. And we're talking about not vectors here in this case, so it's not R2, it's just R. We're talking about x values. We have an x1, that's it. So our domain is all real numbers. Our codomain, or in other words, the possibilities that could come out of here, or we're going to map everything in the real numbers to, again, something in the real numbers. That's our codomain. Now, hopefully, you know that this is a parabola, and a parabola looks like this. And unless we do some sort of shift to that parabola, it's always going to have a positive output, which means that our range, or what we traditionally think of as our outputs or our range, is that f of x is always going to be greater than or equal to 0, right? Or in other words, our range is about half of our codomain. It is only the positive values of real numbers. That's it. So that same idea can be applied to our transformations. So our transformations are a rule that assign our vectors to a new type of vector. Now we could do all kinds of things to that vector, but all that does is says, I'm going to take this vector, I'm going to put it in there. When I get it out, I get a new vector, right? The new vector that I get out is called the image of x. So when I get that tx vector out, we call it the image. So essentially, that's just, what do I get? So for example, if going back to this x squared, if I took f of 2, being 2 squared is 4, 4 is the image of x in this, for this function. So image is a fancy way of saying the values. So here you'll see in this lovely picture, so here's our domain. Now, not always does our domain and codomain, not always do they sort of change sizes, but they could. So you'll see I'm mapping an x value or an x vector onto a t of x vector. So here's our image. And so I could have some other x vector here that could map to some other vector here, right? This is another image. and all of the possible images or all of the possible outputs, right? Again, this is our outputs. Again, we're just, half of linear algebra is just a new language where we're just going to call new names to the same ideas that we've already had, but we're just going to elevate them and upgrade them. So our set of images is called the range, as we would sort of traditionally think of it, right? So in that x squared example, our range is all of the output, the possible outputs are only the positive real numbers. So it's a subset of our codomain. So if we're thinking about this, you ready? If you understand what sets mean, so sets mean a collection of things, and we can use and there's some fancy tools, but the codomain, so the range is a subset. So it contains elements of the codomain. So range is the subset of the codomain. And if we take that a step further, an image is a subset, generally with one element, of the range. So yeah, I was going to come up with an analogy, but my analogy was going to use more math. And all right, to show that a transformation is linear. So now we want linear transformations because we're all about linear algebra here, which means we want everything to be linear. Yay, linear. And so to show that a transformation is linear, we have to show that two properties are true. So the first one says that my transformation should come out to be the same whether I apply it to the sum of the vectors individually or the sum of the vectors first and then my transformation. It also says that if I apply a scalar multiple to my vector and then throw it through my transformation, it should come out to be the same value if I throw my vector through my transformation and then multiply by my scalar. So you'll notice, so keep in mind, remember our order of operations. The C out here says do this first. So do your substitution in there first, or do your whatever you have to do for your transformation first, and then multiply it by a vector or by a constant. All right. So back to this idea of x squared, we want to know, is this a linear transformation? So notice this is not a vector. So we're not talking about a vector equation. We're just going back to a singular value. So it's just an x1. You'll notice that's not bold, that's not bold. Yay, great. So we want to find, is this linear transformation? To do that, I need to show that both of my properties are true. Here's the catch. It is really easy to show something is not true. It is not so easy to show something is true. So in order to show something is true, I have to show that it's true for every single possible x value, in this case, right? So this says, so up here you said for all u and v in that domain. So one says for all scalars and all u, which means that in order to prove this is true, only if all possible u's, v's, and c's make it true. Now, if we just started picking u's and v's and c's and substituting them in, we'd be here all day trying to show that those are true, right? Because I'd have to pick every single possible vector in the planet, and that's impossible. There's an infinite number of them in the real numbers. So we're going to be here all day. The nice thing is it's really easy to show something is not true. So an aside over here, to show that it is not true, to show not true, I only need one counterexample. COUNTER. So what that means is I just need to show that one thing makes it false, and then we can automatically conclude that since I have one condition that makes it false, everything falls apart, right? So that's nice and easy. I can pick one counterexample and I can show that it's not true. On the other hand, we need to be careful. So, like I said, to prove that it's true, to show truth, I need to show it for all. Show for everything. So I want to caution you here. One example that works does not make it true. Just because one works, maybe even two work, maybe three. That's okay. I need to find at least one situation that doesn't work in order to show that this is not true. So, to make it fun, let's start with trying. I'm going to try to make this true, or at least my first condition. I'm going to try to make it true just to show you that it is possible to have a true statement here. So the first thing we want to show is we want to show that t of two different values added together is equal to the transformation applied to one value plus the transformation applied to the other. So I'm just going to pick two values. And I'm going to pick two values in this case, but I'm going to know are going to make things work out just the way I want. So I'm going to do 0 and 1. Right? Now, this is the transformation on just 1. If I add those two things together first, that's what that implies. Add them together first, then put them into our transformation. So this says 1 squared is 1. Right? Now, if I take them individually, the transformation on 0 is 0 squared. The transformation on 1 is 1 squared. And if I take 0 plus 1, I get 1. So these things are the same. But I'm hoping by now you're screaming, that's not a linear equation. That is a quadratic equation. So I've showed that one example works, but is this always true? No, this is not always true. So I'm going to show you another example. I'm going to pick any other numbers, right? 1 and 2. 1 and 2 are going to work for us. So if I take 1 plus 2, that's a transformation on 3, which means I'm going to take 3 squared, which is 9. All right. But if I go back and do these individually, the transformation on 1 is 1 squared, which is 1. Transformation on 2 is 2 squared, which is 4. If I add those together, 1 plus 4 is 5, which is not equal to 9. So therefore, I have a counterexample. So this is a counterexample. I only need that one counterexample to say that this is not a linear. Oh, goodness. Spelling is hard, guys. Linear transformation. So, one time that it doesn't work, whole thing falls apart. Just because one time it works doesn't mean squat. Sorry, hate to say it. So, let me show you what it looks like to actually prove that one of them is true. So we're kind of doing proof light. So we're not actually writing like a 3-step or a 2-column proof. We're not naming all of our things. We're just sort of generally showing that things are true, and sort of making an argument there. So a proof is like an argument, and it's a general argument as opposed to just having an argument. Guys, I don't know what to do with myself. Here we go. So let's look at this example. So I hope you're screaming, hey, look, that looks like a linear equation. Probably going to be a linear transformation. Your hunch is probably right. But we need to show a couple of things. So if I recall, right, we need to show that if I take two vectors and I add them together and then throw them through my transformation, it's equal to taking the transformation on each vector individually and then adding them together, right? So we're preserving that linearity. And then the next one says that if I scale my vector, it's the same as scaling my transformation. And we need to show those. Now, unfortunately, we have to show these things generically, which means I could pick some values, like I could pick a U and I could pick a V with some numbers in them. We could do this, we could show that it works, but that's only showing one case. So instead, I want to show this with my general U and V vectors. Oh, please.
Okay, my headphones have died, so hopefully you can still hear me. All right, so we're going to show this for the general U and V, and we're going to show it for a general C. So here's how this goes. You ready? So notice these are vectors that are just that are size 2. So R2 says that we have a vector x1, x2, right? So 2 elements in our vector. That's it. So our transformation says take your vector, substitute it in, and the way to get your transformation is you're going to take 3 times that vector. So if we use this idea, our transformation on U plus V would look like 3 times the quantity U plus V. And we talked earlier about some properties of our lovely vector properties, or combining and multiplying. And remember I told you, now it was based on matrix multiplication, but it works the same way for scalar multiplication, right? Those were also properties that came up last week when we talked about vectors and their properties. Like, I don't know, let me, if we go back to, if you go back to page 7 in last week's notes, and you look at property number 6, property number 6 says that if I have a scalar times 2 different vectors, that's the same thing as taking 3 times my U vector plus 3 times my V vector. Yay! Now we can take and we can do these individually. So if I take my transformation on just U, well, that's just 3 times my U vector. And if I take my transformation on just V, well, that's just 3 times my V vector. And if I add them up, I get 3U plus 3V. Oh, hey, look, those are the same. So far, this first condition is true. So condition 1 is true. Right, and I've done this for every single U and V. Right, so because I did not actually put in a specific U or a specific V, I've done it generically for U and V. I have shown that those two things are the same. So the next one I want to show is that if I take my C times my U vector and substitute it in, so that would be 3 times my C times my U vector. Right, and that's lovely, which if I simplify this, gets me, so I can do 3 times C times my U vector. Hey, look at that. That's beautiful. Now, I want to see what happens if I take that C after the fact and multiply it by my transformation. So I'm going to have C times my 3U. Oh, that looks a lot like 3C times U, in which case those are also the same. So number 2 is true. So because both of these things are true, we can conclude that this transformation, don't forget your little vector hats, that this transformation is a linear transformation. That is super exciting. Super duper exciting. Hope you're excited. I'm excited. Again, this, if you look at property, so this is property number 6, and this is property number 8 from our properties of vectors on page 7. So head on back there, double check with yourself, make sure it makes sense. Cool. Properties of linear transformations, in particular, the transformation of the 0 vector is always going to be the 0 vector, right? Anything you can do that's going to maintain our linearity is going to say that our 0 vector stays put. Another way of saying this is what this does for us is this tells us that the origin stays the origin. So in other words, we don't shift or move things. This next one says that lines remain lines. Stay, not stat. Lines stay as lines. That's it. All right. Last example has to do with matrix transformations. Now, a matrix transformation, where we have some transformation that is a matrix times our vector, is always going to be a linear transformation. And because it is. Again, if we look back at our properties, right, I told you at the beginning of this week, one of the properties I introduced is that for, where'd it go? Is, I'm losing my mind. I told you vector matrix equations or vector matrix products, that this is always true. A times U plus V is always AU plus AV. Oh, hey, look, that's property number 1, always true. Property number 2 says A times CU is always equal to C times AU. Oh, hey, that's property number 2. Look at that. So because we already know those properties, and they're the same as the properties that make it a linear transformation, we don't have to prove anything. So we can always assume that if we're talking about a matrix times a vector, and that is what our transformation is defined as, then it's always going to be a linear transformation. Okay, so let's use that idea to find some information about this. So first thing we want to find is we want to find TU, or in other words, we want to find the image of U under the transformation of T. All that means is we're substituting, so we're finding TU is just A times the U vector. So, hey, that seems pretty easy. 1, -3, 3, 5, -1, 7, and we're in luck. Our U vector has the same number of columns, or same number of entries as there are columns in A. So I'm going to let you do that multiplication on your own. Pause it, come back. Let's see how you did. All right. Hopefully that was straightforward. Done. Hey. Okay. Next question says, find an X whose image under T is B. If we translate this to an equation, so we want to find some T of X such that the result is B. In other words, we want to find an X value or an X vector that satisfies this equation, which we know how to do. All right? We take our A vector, we take our B vector, we write an augmented matrix with both of them, we do our row reductions, we see if we can come up with a solution here, and that's all she wrote. So we're going to take, and I'm going to put my augmented matrix together. So my 1, -1, -3. I mean, there was a -1 somewhere else. Augmented with our B vector here. That's 3, 2, -5. And I'm going to do my row reductions. And again, I'm going to let you do those row reductions. See what you come up with. And so pause. Come back. See if your row reductions match mine, or if you end up with the same final product. So I'm gonna get this down to I'm gonna get this down to an RREF, just for funsies, because who doesn't love that? And then and we'll make some conclusions from there. So pause, try it out, come back. All right, I've row reduced, did some magic there. There was a lot that happened in between those two things. Hopefully you wrote down more steps than I did. But what this tells us is that our X vector is equal to the vector 3/2, -1/2. And that would satisfy this equation here with that B value. So question 3 here asks us whether or not there is more than one of those X vectors whose image under T is B. So is there more than one solution to AX equals B, assuming that we're not talking about a different B vector in this case? So same A, same B. Well, hopefully you've come up with the answer no, because I had no free variables. Right? We got a single solution, which means that there's no free variables, so therefore there's no other solutions. So no other x values. All right, the last one, 4, says, is C in the range of the transformation? So again, all we're trying to do here is figure out if there is some vector that would when we apply our transformation, A times that x vector, do we get C? So is there some x vector? So again, we're going to set up our lovely system here, or our lovely augmented matrix. -1, 5, 7. Am I over my 20? I am absolutely over my 20 minutes, but you know what? I tried. All right, 3, 2, 5. And for funsies, we're going to skip all the fun parts. And we're just going to get down to 1, 0, 0, 0, -3. Oh, and here's where it gets really curiously interesting. Yeah, this guy. Oof. It's inconsistent. Right? I get 0 equals, or I get, 0 equals -35, which is not true, ever. So, well, no solutions, which means C is not in the range of T. Hey! Cool. That's it. Okay, bye.